Okay, now that you've seen the basic definitions of matrix multiplication, I want to give a different interpretation, which is a little more geometric, of what a matrix multiplication actually is. And we're going to use this in class to do some really interesting factorization of data in an unsupervised way. So let me just go to a pretty simple matrix, one that's just 2 by 2 to illustrate this idea. So this matrix has 4 elements, A, B, C, D. Let me now say that I had a particular vector, x, y, that was a two-dimensional Euclidean vector. Well, I could arrange the components of this vector into what's known as a column matrix. So I could put the x component in the first row, y component in the second row, and there's just a single column. So that's another way of representing the same data. But if I represent it this way, then suddenly I actually have a matrix which can play with my other matrix, my 2 by 2 matrix. So I can actually multiply my 2 by 2 matrix on the left by this column vector. And that's a 2 by 2 times a 2 by 1, which gives me a 2 by 1. So that in particular is the vector ax plus by for the x component and cx plus dy for the y component. So you can really think of these as functions from, in this case, two-dimensional vectors to two-dimensional vectors. Now, if I factorize this a particular way and I color the columns, you can see something pretty interesting here. So here's a little picture of what's actually going on. So if I break apart this sum, ax plus by, cx plus dy, I can break that apart into a scalar times a vector ac plus a scalar times a vector bd. So I can say that any vector, when multiplied by this matrix, is a scalar, which is the x component of that vector, times the first column, plus a scalar, which is the y component of the vector, times the second column. So what I'm really telling you how to do is a vector sum of the first column and the second column. So I give you my x that walks along the first vector, so that's my first column, AC. I give you a y that walks along the second column, and then I add them together, and I get this vector here. So just for a concrete example, oops, it didn't like that. Here we go. Let's say that I had the matrix 1, -1, 1, 0. Then I could say, okay, well, the first column is the vector 1, 1, which points up here like this, and the second column is -1, 0, which points over here. So my x component walks me along this diagonal, my y component takes me to the left. And so if I happen to multiply by, x equals 1, y equals 1, then I walk up here, I walk to the left, and I should get the vector 0, 1. And if I check that, I would say, okay, 1, -1 times the vector 1, 1. So that will give me a 0 in the x component, and that will give me a 1 in the y component. So again, just to recap, matrix multiplication by a column vector can actually be thought of as a vector sum, or what's known as a linear combination, of the columns, where each column is a vector that's weighted by the corresponding component of the vector. So here I'm saying the first column is weighted by x, plus the second column weighted times y. And there's this very nice geometric interpretation. This also works in higher dimensions. So let's imagine that I was in, we'll say 4 dimensions. I'll create a vector. Let me say first vector is 1, 1, 0, 1. I'll create another vector. I'll say 1, 0, 0, 0. And then I'll create a third vector. So these are all in 4 dimensions. I'll make my third vector be 0, -1, 0, 0. Okay. Now I could do the following. I could say, okay, well, I'll make x be 1, y equals 2, and z equals -1. So I could say, okay, well, what's the sum of x times v1 plus y times v2 plus z times v3. And I get, okay, so that's the vector 3, 2, 0, 1. But the other thing I could do is actually line these vectors up as columns of a matrix. So I could say the following, okay, well let me make a 4 by 3 matrix. So I'm in 4 dimensions, so I want to have as many rows as there are dimensions. So I'll make a 4 by 3 matrix. I'll make the first column be the first vector. So this is saying take all the rows in the first column. That's the first vector. I'll make the second column be the second vector. And I'll make the third column be the third vector. So far I've just copied the data over into different format. But now what's neat is I can say the following. So if I print A, the matrix multiplication of A with the vector x, y, z, NumPy will automatically know to turn this into a column vector. It figures out the context. So this is a this is a 4 by 3 matrix. So I'd be multiplying by a 3 by 1 column matrix. So NumPy sees, okay, there's 3 dimensions. They must have been a column vector there. So anyway, you see I get the same result. So this says, okay, take x times the first column plus y times the second column plus z times the third column. And that ends up giving me the exact same result. Now, this is a float instead of ints here, but same result. All right, so that's how you can use matrices to actually do vector sums. And so what we're doing in this unit is thinking of decomposing our data into these kind of principal components or little dictionary elements. And we want to be able to add those dictionary elements together to make your face or a tune or something else. And so we're going to make up a more complicated thing from a lot of simple things. And a nice framework for doing that is to put the simple things along the columns of a matrix and then just say, well, what vector do I need to multiply that matrix by to create my complicated thing? So here I wanted to create the vector 3, 2, 0, 1. Here are my components. And I told you, hey, if you stack these components up in a matrix and multiply by these weights, 1, 2, -1, then you can get this vector. All right, so I'm just going to have you do a quick exercise on that. And then in class, we're going to do something called non-negative matrix factorization, where we actually learn what good columns would be from data.